Hey guys, welcome to the second video where I'm going to be talking about electromagnetic radiation. Before we get into electromagnetic radiation, let's talk about one more thing about waves, their speed. You must have heard about the speed of sound and how sound is carried through waves. And the speed of sound is really fast. It's so fast that it's almost kind of impossible to think about how it was measured. How could you even measure something that travels so fast and can't even be seen? Well, let's talk about it. How did scientists calculate the speed of waves? Well, we do know for sure that speed is equal to distance over time. So let's look to our wave to see what things could fulfill our distance and what things could fulfill our time. Well, the only distance E kind of related thing in our wave is our wavelength that we talked about earlier, which goes by the Greek symbol lambda. So what I'm going to do here is I'm going to replace the distance by the lambda, and this symbolizes our wavelength. Now that we have the distance in our speed equation, we need to figure out the amount of time it took to travel that distance. So, what is the amount of time that it took to go from one point to another point? What is the amount of time it took to go one cycle? Well, in our previous video, we discussed that that term was called the period, and that is replaced by the letter T. The time portion is replaced by our period. Perfect. But let's go ahead and dig a little bit deeper into this. In the previous video, we discussed how the frequency of an equation is equal to 1 over t. 1 over the period, I should say. Now, let's continue on with this equation and let's develop a little bit more. Let's try and get period on one side. So what we need to do is multiply by t on both sides. We get v times t equals 1. And now, to get t by itself, all we have to do is divide by v on both sides, and we get 1 over v. So the period is equal to 1 over the frequency. So now that we have this t term all by itself, let's go ahead and replace it in our speed equation. So all that we have to do is, let me rewrite it down here actually. So we know that our speed equation equals lambda over t. Now that we know what t is, let's replace it with 1 over v. So what I'm going to write here instead is lambda over 1 over v. Now, if we simplify it, I'm going to draw a big arrow here. If we simplify this equation, what we can see is that speed equals lambda, wavelength, times v. So, in other words, the speed of a wave is equal to its wavelength times its frequency. Now we're good to talk about electromagnetic radiation. Light is the most common form of electromagnetic radiation. Through previous experiments such as the double slit experiment, it's been shown that light has wave-like properties. Now, in order to keep this video brief, I'm not going to talk about the double slit experiment, but I've linked a really good video by the Science Asylum that talks about the double slit experiment and why light behaves like a wave. Since we know that light can behave like a wave, that means that we can know what the speed of light is just by taking its wavelength and multiplying it by its frequency. And we do know what the speed of light is. We know that the speed of light, which is coined using the letter c, is equal to 3.0 times 10 to the 8 meters per second, which is pretty fast. In fact, nothing in the world can ever go faster than the speed of light. However, it isn't just light that carries the speed. In fact, all electromagnetic radiation has this speed. Electromagnetic radiation falls within a spectrum. The most important spectrums that you should keep in mind are classified using the wavelengths between 400 nanometers to 700 nanometers. This is considered the visible light region, which is the color that our eyes can see, hence the name visible light. Beyond this 700 nanometer region beyond it is the infrared spectrum. Infrared waves are usually felt by us through heat, and just below the 400 nanometer spectrum is the ultraviolet or UV region. The UV region is probably most experienced when you're getting a suntan because the sun emits UV rays. Now, we can't see either the UV region or the infrared region, but we can definitely feel and sometimes see their presence if we get a sunburn. The visible light spectrum falls within the rainbow of colors that we can see, with blue falling towards the 400 to 420 nanometer region and slowly increasing up towards red in the 700 nanometers region. It's important to note that the electromagnetic spectrum is not just composed of visible light. In fact, visible light only takes up a very small portion of the overall electromagnetic spectrum. Once you get past the infrared region, you have things such as radio waves and microwaves. You've probably dealt with those when you're at home. Once you go below the UV region, you have things such as X-rays. If you've ever broken a bone or gone to the dentist's office, you've probably experienced X-rays. And just below X-rays, you have gamma rays and cosmic rays, which are waves irradiated throughout space. So all of these waves fall within the electromagnetic spectrum, which means that they all have the same exact speed of light, 3.0 times 10 to the 8 meters per second. So don't be tricked. Whenever someone asks you if there's a difference between the speed of radio waves or gamma rays, you can easily tell them to their face that no, there is no difference. They all travel at 3.0 times 10 to the 8 meters per second. Although I highly doubt that anybody would just walk up to you and ask you that. Unless they're a chemistry teacher, of course. So that wraps up this video. Thanks for watching, and I'll see you in the next one.